Are we recording? Yes, great. Okay, then welcome back, everybody. Welcome to our today's evening lectures at OPSO 2022. So I'm very happy to announce our next speaker, Erik Bollt from Clarkson University. And he's going to talk about, no, where's the title? Next Generation Reservoir Computing. Do I pronounce this correctly?
Okay, hello. So thank you for having me. It's very exciting to be this end of the day lecture. This is roughly the title. I forgot exactly the title I gave to you, but it's mirrored after a paper I had last January, which for me was uncovering why this machine learning method was so successful. And it turns out I found a strong connection to NVAR. I'll tell you what that is in a little while, and then also some transfer operator stuff. And that eventually led to last fall an improved version, which was a Nature article with my friend Dan Gauthier and his gang. And there's a connection which I haven't even told to Sudham yet. You saw Sudham perhaps last 20 minutes ago talking about something else, but this is Sudham's paper about random projection methods for dynamic mode decomposition, which is a Koopman operator data-driven method. And I want to point at my book generally on these things, but mostly for Bernays-Prone operator. That's from 2013. So I'm at Clarkson University. I'm director of this group that we call the Clarkson Center for Complex Systems Science. This is what we look like from the air in the fall. We're in upstate New York. There's rivers right up here, and just at the horizon is Canada. It's about 15 miles away. And this is the university, and I'm sitting over here at my house right on the river. And so for our friends in Russia, it was minus 26 today, Celsius this morning. And this is this past weekend. And it's very nice in the woods here. I like to cross-country ski. All right. I can't go. My slides won't change. 1 second. All right, here we go. Okay, so it's sometimes fun to start with the conclusion first, or a conclusion first, to give you an idea of where we're driving to, because I'm going to say some theory and development, how it all works. But it's this whole thing, reservoir computing, and then our improved version, NGRC, next generation reservoir computing, is a less data-hungry way to do forecasting. So I'm going to show you a linear version, a linear interpretation of reservoir computing with nonlinear readouts, because that'll let me get after NVAR, nonlinear vector autoregressive modeling, because there's a well-developed theory underneath that comes from our friends in econometrics and a Wold theorem. And this will lead also to besides the theory paper, which was my first paper, an improved version. So this is what it's capable. So vector autoregressive model versus a vector moving average model is what supports the Wold theory for instant existence theory. So this is the kind of thing we can do, which is, here's the famous Lorenzo tractor. Here's 3 time series from Lorenzo tractor XYZ. And in a training phase, we make our model, the RC, reservoir computer, match to the true, so that in a testing phase, we give it the same initial condition and we just run it, and then we'll compare it post hoc to true data. And the red tracks extremely well to the blue for a long time. And that's interesting. And of course, you don't expect it to track forever, because even if you had the real model, you still have sensitive depends on initial conditions. What's really striking and exciting for this kind of model is even once it starts making the error, it makes what we call good errors, because it still tracks the measure somehow. So people in this field call that it captures the climate. So notable literature, what we end up doing in NGRC reminds me a lot of what's called NARCS, what I call NVAR, which is a well-developed theory by the Billings group. And there's some beautiful theory for reservoir computers by Ortega's group with Gonin and Ortega that an RC can be interpreted as a universal approximator. So NGRC, it's simple, it's much less data hungry, not too many parameters, and it's flexible in its features you've input. So now I'm going to tell you what an RC is. An RC is a kind of machine learning method in the field of neural nets called a reservoir, a recurrent neural net, RNN. And this category is particularly good for time series forecasting. Works really well. So it's a kind of random RNN, and a lot of people have been showing how well it works and improving it. And I was really wondering, why does it work with all these random parameters? Because it's essentially a random RC. And I'll give you the details on that in a minute, but this is kind of a general neural net kind of picture you show, which is you input data, in our case, vector data through dimension dx, so it's for Lorentz, that'd be 3. And then you input it into some kind of neural net, and then you have a readout layer where you read out next outputs. And what makes RNN interesting is it's not just feed forward, you have the neurons have connections back and forth, as opposed to just feed forward. So the punchline I realized over time is even though you pick these weights randomly, somehow time soaks up the random stuff. So I'll show you what I mean by that in detail. And then I find the equivalence to NVAR, a bridge that bridges to econometrics theory and the Koopman operator. So this is how it works. So this was put forward by Jaeger and Haas in 2004, and Jaeger under a very similar thing called Echo State Network in 2001. And this is how it goes. So give me a bunch of vector valued samples. So lots of samples from Lorentz, for example. And you want to read it into a network with a random read-in matrix, and then you're going to advance it with a random interaction matrix A. And by random, okay, so you input X of dimension dx into U variables by a read-in matrix, and this guy's typically not square. So Wn will be dr by dx. Dr is typically much bigger than dx. Like if this is 3, people typically use like r is 1,000. But you pick the weights randomly. And then once I have that, I'm going to use that as kind of a forcing term for an internal state R. R is the internal state of all the neurons at a given time that I'm going to advance by a matrix A, and A is also random. So this will be dr by dr, and choose it also by some random distribution, and which distribution to choose, that's kind of a how-to in little cottage industry people do. And then once I do that advancing with a bias, perhaps a random bias, then you hit it with a threshold function. So typical threshold functions like some kind of sigmoid function, ReLU function is very popular. I'm actually going to simplify this for my analysis and just do identity function initially and interpret that, knowing that the identity function for small values of S looks a lot like the threshold function, but it doesn't have that saturation aspect to it. And then when you're done, you read out into the next values of X. And a normal neural net, what you would do is you would train all the parameters, lots and lots of parameters, A, B, W in, W out, tons of parameters, and you fit them. And since there's this nonlinear function Q typically, then you have to do some kind of gradient descent, and there's other kind of versions of how to do that in the machine learning literature. So you train tons of parameters, and then you should start worrying about overfitting your data. And it's an amazing, cool technology that you can actually fit so many parameters and get something useful, but that's clearly what's been happening in the machine learning world. What these guys realized is, wait a second, I can just pick these read-in weights and the internal weights completely randomly and only train the output layer, and it still gives something useful. And it actually works astonishingly well. And then the other part is the readout is trained as a simple linear regression problem. And so it's easy to train. So that's easy to train is clear. That it works was really a surprise to a lot of people for a long time. And I saw this first starting about 5 or 6 years ago, and I thought it was silly. So I just didn't even really look at it. But then I saw Ed Ott talk about it at a conference in Dresden about 2.5 years ago. And he was really convincing that it works and was using it a lot. And I really trust his sense. So I thought, I got to look at this. So I'm going to try, first I'm going to do is try to program it up and see how hard it is to do. And I thought it'd be a pain in the neck, but then I did it on the airplane on the way home over the Atlantic, and it only took about 1 hour. And I don't know if you've ever worked with these kind of numerical algorithms, but typically when there's lots of parameters, you have to tune them just right, and it barely limps along and it barely works. And then you say, okay, they kind of they cherry pick the good case. It's not the case here. Like it worked instantly. It worked for a really wide range of parameters, and it was really easy to make it run, even despite all the randomness. Okay, so that's the algorithm. It turns out that's equivalent in a certain version I'm going to show to something famous from econometrics called autoregression, or the vector version of it called vector autoregression. So this is what a var-k is. A var-k is a linear stochastic process where, okay, think of a time series where I'm sampling at y's, and then I have the y sampled in delays, and you add them up with weights, and you're perhaps forcing it with noise. This is what a vector autoregressive process is. I mean, an autoregressive process. And this is an RP written this way. And if these are vectors, you call it a var P. And of course, you can have a var infinity. So these are examples in R1 and R2. The V just means vector. I need to get rid of these markers like screen sharing because it's covering up my own talk. 1 second. Okay, there's that. Okay, good. No, it still says I'm recording. I'm sorry. 1 second. I'm just going to move that out of the way. Good. Now I can see my talk. So in different, like for this example right here, here's a very simple example that generated these versus this example that generated this. This is in 2 delay, so it's an R2 with epsilon white noise. So depending on the weights, you have different kinds of versions of ours. Like if phi1 is 0, it's a white noise process. Phi1 is 1, it can be interpreted as a random walk process. With C not 0, it's a random walk process with a drift and so forth. Okay, so this is what I mean it does well. This is just a standard reservoir computer fitting to Lorentz, and red is the fit, and it fits for over several Lyapunov times really well in a forecasting mode. This is you feed same initial condition and you run the true just for comparison, and you run the model. Of course, you would never have the true for comparison into the future, and for quite a while they match. And this is errors, and error grows over several Lyapunov times. It does quite an excellent job. Okay, so my question was how it works. That's well set. It's why it works. So other people have been putting lots of work into trying to make it work better. So how to better pick A. So typically you have to do something about controlling the spectral radius. And typically people have been choosing A to be sparse. You know, so I just chose it from uniform distribution just for discussion's sake, but you may want to choose it, say, from some binomial process so it's sparse. And how to do a better read-in for W in optimizing over those parameters and so forth. That's kind of the engineering of it that people have gone through. I'm going to strip away all of that and just choose uniform distributions. And I'm also going to choose that threshold function to be identity function for a while because it makes the analysis easier and it still works. And like I say, then I'll have a strong connection of R, which connects to VMA that has the Wold theorem. Then that ends up connecting me to Koopman, and I've kind of been in kind of a fun mood lately, and everything Koopman I spell with a K, even if it's a C, so connected to Koopman. So I'm going to call the inner variable once it's read in R. So once you read in the X's, you have a bunch of R's, and I'm going to think of collecting all the R's as a big R matrix. So then the readouts, I'm going to call Y sometimes, but sometimes I'm going to call them X. So I'm going to use the Y's and the X's almost interchangeably because they don't have to be the same variable, but if I want to feed it back in, then they do have to be the same variable. So I'm calling it Y, allowing it to be different, but X sometimes because I want to then make it run itself. So R's will read out to X's by some readout matrix, which I'm going to call temporarily V before I know its value. But once I've got a good value, I'll call it W out. And so W out should be the R's after you do the readout matrix V, and you should compare it to the truth, the X's, by minimizing this over some norm. So Frobenius norm is what we use. You could use different norms as a different inverse problem. But if you use the Frobenius norm, it's essentially a least squares problem. There's a lot of parameters, so you're in grave danger of doing overfitting. So one way of handling overfitting is to regularize the problem by adding something that penalizes large values of E. And then that leads to, if it's an L2 norm, it leads to the Tychonoff form, the Tychonoff regularized form called ridge regression. And this is the ridge regression solution of this problem. Okay, that's well established. That's what people do. Okay, so if Q is like a hyperbolic tangent, this is how I guessed this concept in the first place. I looked at the hyperbolic tangent and say, hyperbolic tangents, if the data doesn't run away off to infinity, we'll never end up using the threshold. So that would be the goal. So people typically choose A to be of not too big a spectral radius so that it wouldn't shrink to 0, so not too small, and it wouldn't blow up to infinity too big. And you wouldn't end up always punching onto the flat part of your threshold function. So if you can do that and kind of balance it, so the throw always hangs out in the middle anyway, so the hyperbolic tangent ends up looking almost like an identity, and we would know that through its Taylor series. So that was my guess as to why I should go this way. This is what these inner variables, the inner variables look like for like the Mackey-Glass equations, which is a differential delay equation. Here's a training time series of that differential delay equation. Here it is blown up in time, so just a short segment of it. You can see it's a short time segment from here to here. And simultaneously, I'm showing you some of the inner variables are, the reason there's about 1,000 of them for this particular example, but if I show you all of them, it looks like a mess. So here's about 7 or 8 of them, of the inner variables that are running hidden from the output layer, but they're inside the machine learning algorithm. Okay, so if I choose the identity matrix as my threshold, then the algorithm just becomes this. Remember, okay, so go back here. Remember, I said this was the algorithm, possibly with a regularizing term that balances the machine learning part and something that resists the threshold. That's kind of the full form, but I'm going to choose alpha equal to 1, so this part goes away. So I'm just going to show you this and iterated on it when Q is equal to identity. So in other words, the Q essentially is not there. You just have the stuff in the parentheses. So I'm going to just iterate on this and make next R's. So if I choose the first value of the inner variables to be 0, then, and I'm going to use in this notation to be the read in first value of X. Remember this Wn is random matrix. Then R2 is simply this equation with R1 is 0, it's simply the U1, so it's simply the read in value. Great, now grab that and plug it in again and read in the next X and call it U2, and that's this equation. That's my R3. And then grab that and place it here as my R3 and hit it again with an A and read in the next value. So you just kind of keep distributing the A's, and R4 looks like that. And keep going and going and going. And you've got a sum of things. That linearity is great because you can distribute. So RK is just this through read-ins. And A0, this notation I interpret as identity. Okay, that's kind of the main initial trick. And with that, I say, okay, what if I hit with a readout? Now hit those R's, which I had as a summation notation with a readout. I made a typo. There should be a W out right there too. So W out hits all that stuff, and then it distributes, just expanding the sum. I have all that stuff. And then I just draw a circle around this, and I draw a circle around this. And I say, you know what, this is just some matrix. W in was dr by dx. Dx is the size of the true variables. This is dr by dr, and this is dx by dr. So this whole thing is dx by dx, and that's a matrix called the kth matrix. And each of these guys are matrices. So I have a bunch of matrices. So through K, I just have a bunch of matrices times the data. And that's what this says in the box. Each of these matrices is that expression where that's a random matrix and that's a random matrix, and this guy I train. That's how you do this is what is happening when you do a standard reservoir computer with all the random stuff selected, only training the output. And you choose QX equal to X. And then I look at that and I say, you know what, I recognize that. That is a var. So I'll remind you, a var K, a general var K would be matrices times time series in vector valued X. And I have essentially the same thing, except forced by noise. But we'd expect noise in truth in this. The noise could be either thought of as the skipped terms, or actually, instead of a deterministic system, it might be a stochastic process. And the general var K allows for a bias. So writing this, now I have some understanding of what's going on with the reservoir computer. In general, you're just really doing this. And then you ask, okay, why am I selecting this random matrix anyway? And why am I selecting this random matrix and training on that? Why not just train on the whole thing and fit the A's and just go straight after a var K? So the punchline is going to be that a reservoir computer, a working reservoir computer, some random A's, sometimes you pick a random A that just doesn't work, it's a dud, but most of the time it works with high probability. So why go through all that work? Why not just use its equivalent form, which is the var K? So another version of this is to say that a var K is underlying any working RC with all those random parameters. Another way of saying it is that each time I'm iterating, I'm kind of soaking up some of the randomness of the A. And so after I have enough iterations through all the column space in A, you've sort of picked out all of the randomly selected values, and that's why it's working. I have a fading memory interpretation of that story. Okay, so I'm going to rewrite this equation for each K and essentially making columns out of the X's. So just state this again for the next K and the next K and the next K, and it looks like a big matrix. So XK through X1 times all the A1s through AKs. These are matrices. There's some matrices. So this is a big matrix, and this is a column vector. And I get the first output value, And then in the next time, notice I'm shifting the time, I get the next output value. And this X and this Y will generally be the same size. And when you're going to feed it back in, remember I call the Y's X's again. So this would be a K minus, no, N minus K by dx matrix Y, which I'm actually going to call matrix X. And this thing, each of these columns is dx by 1, and I have K of them. So this is dxk by 1, a column vector, and I've got this many columns. And I'm going to call this guy script dx. And solving this problem for the A's can be solved as a least squares problem, but regularized by Tychonoff regularization. So I call it A star, which is this matrix solved in least squares, but regularized. So that's A star. And you just left multiply. I can think of it as left multiplying by the pseudo inverse, the Penrose pseudo inverse. It's the same thing as doing least squares. And the lambda means the regularized Penrose pseudo inverse. And that's what's well formulated. Okay, and the A's are just the elements of this guy. I can interpret this in several ways. I can draw a circle around this thing right here and call it my A. So my W out is just part of this expression. So I can extract the W out. I can write A as the W, this A, this script A as W in after you hit it with a bunch of your A's. So that's one way of thinking what the A matrix is. If I need that, but by saying maybe you really should be skipping the reservoir computer formalism, this is just for a discussion of the equivalence, because the equivalence to a var means there's a little a sitting there, an A star. So this essentially shows in the linear case that an RC and a var are the same thing. Well, through the interpretation. So doing it just this linear way, it already works pretty well. I'm going to make it better in a second. But this is what I mean by works pretty well. So take the Lorentz data, which is blue, and fit it with a linear reservoir, and then just run it out into time in red. And so for a little while, well, so 2.5 seconds, it matches quite well. And here's the error. But after it starts going bad, it starts doing other stuff. So the linear one shouldn't be a surprise. The linear one doesn't reproduce the invariant measure, doesn't reproduce the climate, but it does do good forecasting. And that's what the econometrics people already told us, that a VAR can do good forecasting. And I say, don't do the RC away, do the VAR away anyway, because you can just compute the A's directly. Okay, the reason though that you would want to show it's equivalent to a VAR is we have the Wold theory from time series forecasting from econometrics. So I'm just going to repeat the Wold theory. It's an existence theorem. So when you have a process of zero mean covariance, stationary covariance vector process, there exists a VMA, possibly of infinite history. But that possibly infinite history hopefully has a vanishing memory, and you can estimate that guy by a VMA K. Okay, that's the theory. So that's what goes on in the theorem. It says there exists a representation like this. So it says X at time t is possibly some kind of delayed combination of a random variable XCT, white noise, plus a forcing term, which is called innovation in this field. So this CL, I'll just show you what that is by example. So take this as my CL on a time series XT. If I have this as my process, X at time t, X at time or previous t, X at time t, the other variable X at time t, the other variable at a delayed time, and then the other component, X at time, the other last time, the other variable to last time. This can be written in delay notation as a big matrix times these guys. And then a matrix like this can be decomposed into parts that are matrices with delays. And you can write series of these things. So that's what this notation means. And it may be an infinite moving average representation. So this is a VMA, and the Wold theorem says such a representation exists for a rather broad class of stochastic processes, and that's great. If this thing has some properties having to do with the spectral radius and boundedness, you may be able to invert it, which means take this matrix and move it to the left side. And on the left side, I'll call it BL, which is essentially the inverse of that guy. And there's details on how to make that work, but that's sort of the goal, is to move that to the left. And if you move it to the left, then I call this thing a VAR. So that would be a VMA, and that would be a VAR. So moving average model, autoregressive model, and sometimes you might make a mixture, and those are what's called ARMAs, autoregressive moving average models, to kind of get parsimony, which means balanced. But for my purposes, I show that the RC was equivalent to one of these guys, which when that guy's invertible is equivalent to one of these guys. And running it the other way, I say, when can I run that process the other way is when this exists. Wold tells us when it exists. So Wold tells us, therefore, in some cases, when this would exist, and then the RC. So that's sort of what underpins a lot of the theory that's in my longer theory paper. That completes that section. I claimed an RC is also reminding me of Koopman as a DMD. So remember I showed you a little bit ago, I showed you this expression. Well, this thing right here is just a stacking of the data. So if I take this like x1, x2, x3 through xk, x2 through xk plus 1, xn minus k minus 1 through the last data point xn, and stack it like this, I can think of advancing it by a matrix. Well, I am advancing it by this little matrix, which is var. But this is what you do in a Koopman version of the story. I think of a general matrix K that makes not a single row, because remember over here, I had a single row of these X vectors, but all of the next times. So in a same size stacking. So this matrix is basically this matrix, except you see I've indexed it by 1, and I've indexed the bottom row by 1. So it's very similar. These are called, in the DMD literature, this version of Koopman, which advances it by a matrix, is called Koopman havoc. I've just forgotten what the acronym havoc stands for. It's HAVOK. It'll come to me later. So guessing a matrix K that would do this advancing or computing it somehow is what you would do in Koopman, but this K would be K times dx by K by dx, where this A matrix would be dx by K times dx. So these aren't the same size, but solving this guy in least squares and solving this guy in least squares, this is what one does with DMD, kind of show a relationship between them. Okay, so I find that interesting that this reservoir computing algorithm reminds us a bit of DMD, and I'm going to try to hint of where a random version of this comes in a little bit. Okay, so just in practice, remember I showed you the linear works pretty well. What actually works fantastically well is doing everything I showed you except with the linear reservoir, which means that Q of X is simply X, a linear activation function, as opposed to a ReLU or hyperbolic tangent, but do the readout possibly as nonlinear. So this is a quadratic readout, and I'll show you the details of what I mean in a minute, but let me just convince you that it works fantastically well. A linear RC with a quadratic readout, which is quite different from what most people in the reservoir computing community do. They typically do a linear readout, but a nonlinear activation function. And again, I do it my way because I have a theory underpinning it. And then it turns out it works efficiently too, but I came to it from the theory. Okay, so it works really well. Even though this does pretty good short-term forecasting, this does better short-term forecasting to a little longer into the future. But also exciting is once it starts making errors, it makes good errors. So by good errors, the red is the forecast just from an initial condition, and then you never show it data again. It makes something that reminds us a lot of Lorentz butterfly. So it reproduces the climate. Its invariant measure looks like the true. I'll show you what I mean by linear readout and nonlinear readout in a minute, but this is just a slide about vanishing memory. So remember the A's are the var coefficients, which I can get directly by computing the A's as I showed you. And so since AJ is this expression, I can ask how big that is, and it's bounded by just breaking out the matrices. I'm going to bound it in nuclear norm, which has to do with its singular values. And anyway, the point is, if that guy is pre-picked, that guy is computed, then this guy in powers, I can also break the powers out, and it's related to the spectral radius. So whatever the spectral radius of this guy, you raise it to powers, and these must decay in powers. So that's sort of a bound on how big these would be, and that's a description of how your memory fades into the future. But in practice, the fitted A's in norm tend to fall off rather quickly, depending on the process. So the Mackey-Glass equation I showed you, the A's don't seem to use much past 6, really much past 5. From the Lorentz equations I showed you, the A's, somewhere between 5 and 6, it seems to saturate to small, but there's kind of some persistent noise I can't seem to capture until much smaller. Okay, let me show you what I mean by a nonlinear readout. A nonlinear readout is take your inner variables R, and I'm also going to form, so I'm going to call that R1 now, a matrix of all the inner variables over all the times I'm building data. And I'm going to build all of the quadratic terms. I could also build all the cubic terms and all the quartic terms, but I'm just going to show it to you for all the quadratic terms. I'll call it R2, all the quadratic terms. So these are Hadamard products. So the Hadamard products, okay, so let me show you what the Hadamard product does. So the Hadamard product between two vectors, when I hit it with a matrix B, so B times a W, a vector W, B is a matrix. I can think of the B's as having column vectors. So the bold B means all the column vectors of the B matrix. So this is this expression, so I mean one of these guys, which and W1 would be one of the entries, the first entry of the vector W, W2 would be the second entry of W, and so forth. So this is just an expansion of this into its column form. And a Hadamard product to the same thing would look like that. And you can show that this expression gives Hadamard products between all the B columns, which just means component-wise multiplication, times the W's in all the quadratic terms. So when I write this, it's like picking up all the quadratic terms. You know, W1 squared, W1, W2, through Wn squared. And so writing that, I'm going to say, call this thing, all the quadratic terms, that's what this means, polynomial 2, means all the monomials, the vector of all the monomials of the vector W. So this is if W is n-dimensional, then this vector W2 is n square dimensional. And certainly there's repeats, right? You have, because W1, W2 is the same thing as W2, W1. That's commutative. And all the coefficients, I'm calling it big P2. Okay, so if I form this vector and this being all the monomials, I can make a big matrix R, and I'm going to train the W out based on that. Right, so the idea is you run your reservoir computer as I was before, collect all the R's, but on the training phase, I'm not going to train it just on this. I'm going to train it on all the quadratic stuff and call that big R. So W out will be trained on the whole thing. And then I'll abstract the W out into the component matrices. When you do that, I can ask myself what's R2, R2, R3, R3, and a very similar thing happens in the linearity. You can track it through the Hadamard product, and you get expressions that reminded us as sums just like before, except now there's sums in the monomials and whatever this thing was that keeps coming out, but with the A's hitting it in powers. So that's essentially going to be the punchline, which it turns into an algebraic hairball, but it's okay because you can track it through. And anyway, at the kth stage, you get Hadamard products like this, which it basically in the end expands into linear combinations in quadratic terms, all the quadratic monomials and matrices. So then I'm going to call this whole thing expression A2 of X because the X's enter. So that's the A2s. And then you still have the A1s as before, which was the linear terms. So that fitting seems like a mess, but it's for equivalence. But what you really do is you take all your data, I'm not going to call it X1, you stack it. Then you stack all the quadratic terms, all the monomials. You stack those, and this is big. At each time, that's columns, call it X1, X2. and that X. And then the next output value, this Y would be the same size as the X, not of the whole thing. So Y would be some A times this massive X, this massive X, and A will consist of what I had before, which is the var terms, and then all the monomial terms. So this is a doubly indexed matrix. See, so that's what this says. A's are what I had before, plus W's times the coefficient matrices that depend just on the read-ins, times the inner variable. So this is all quite workable, and that was nice for the theory, that the equivalence between an RC with the randomly selected A and doing this stuff, and now I'm going to call this stuff NVAR, which means nonlinear vector autoregressive modeling, is an expression like this. And of course, you can include cubics and quartics and so forth, but writing it out in this kind of cumbersome way is for connecting the two theories. It's not for how you would actually do it in practice, but that's where I left it in my first paper from last January. And then this starts looking a lot like what's called NARCs by the Billings group. Well, I was showing this at a talk about a year and a half ago, that much, and Dan Gauthier contacted me. He's at Ohio State, and we started talking, and we realized, okay, great, skip all that now, and instead of doing an RC, let's do the NVAR way, because a working NVAR implies a working RC. So we don't really need the RC anymore. We don't need to select all those parameters, those random parameters, and we don't need to tune it. We just kind of get the best fitted NVAR, and it will be an RC. And then we realized a nice compact notation for developing all those monomials that's built out of Hadamard products, which is kind of like multiplying things in all different combinations. Kronecker products and Hadamard products. This one particular one's a Kronecker product. So suppose you had some process and delays, and you wanted to collect all the linear terms, just it's a stacking of them, and all the nonlinear terms, perhaps through several monomial layers, and we collect the whole thing, and we should just fit the readout parameters and just be done with it. So I'll show you that more in a minute. This is a slide stealing from him. This is Lorentz, but he was thinking in terms of its origin form, which is the convection layers in the atmosphere from the Saltzman's equations. Using only the quadratic terms, we already got a really good fit to this particular process, but actually there's this square bracket around it. We interpret it as uniquifying it, right? So that we don't pick up X, Y, and Y, X. We just combine the two into X, Y. So the unified version of the all the monomials. And it does a fantastic job, which I'll show you in a minute. Okay, so this polynomial expression brings us from the right size spaces. Okay, so as I spoke, I'm going to mostly skip this one and get to, I have another summary one in a little bit. This is the slide I showed you almost at the beginning. It works really well. So when we do this thing with the Hadamard products and the Kronecker product to develop all the excuse me, all the monomial terms for nonlinear readout, and just go to NVAR instead, we call that NGRC. And it works fantastically well, as this trained NGRC shows or describes. It's really simple to do in the end, even though the theory underlying it is kind of intensive to write out. The code to write it is shockingly small. Like in MATLAB, you have a built-in Hadamard, you have a built-in Kronecker product, so you just put it all together quickly. It's very not data hungry. It doesn't take a lot of data. There's almost no parameters to tune. There's only the regularization parameter in the Tikhonov form, and it's very flexible to what features you may want to put in. And that's essentially what came into this paper of ours last fall, which we call NGRC, Next Generation Reservoir Computing. And the punchline is linear reservoir computing with nonlinear readout equals an implicit NVAR, which was my original single author paper. And then that motivated us to make an efficient form of doing the NVARs, which we now call NGRC. And when you do an NGRC, it has an implicit RC. but it skips the middleman. And this is kind of the summary graphic for the whole thing. This is how you would do forecasting, say for Lorentz, forecasting and training through an RC if you're doing it the reservoir computing way. You would form these random matrices, you'd pick a threshold function, you'd pick biases, you'd pick sizes. What dimension should this thing be? That's sort of a hidden parameter. And this is often very big, like 1,000, even though this might be 3 or several thousand dimensional. A threshold function, some balance to the internal variable, do the fitting, fit the W out, read out the value, and hope it works. And sometimes it doesn't, but often it does. The NGRC way is you take the same data, you form all the linear terms, you form all the nonlinear features, which in Lorentz, it works really well just to pick up all the quadratic terms. If you didn't know that, you would just pick through high order polynomial, stack them, and fit the W out directly to the stacking by some kind of least squares process and just use that for forecasting. It's very quick and easy. And that's everything I just said. So Ortega had a paper that tells us that a reservoir computer with nonlinear readout actually it also manages to do a universal computation. It's a good representative for a general stochastic process, and that was also what was in my paper beforehand, and now here we were doing it. So here's some tasks it does well. So predicting our Lorentz it does well, kind of a lot of other examples. Here's a double scroll oscillator. Another kind of task would be, let's show it, train it on Lorentz data, XYZ, so that the input is just X and Y, and the output is Z. So I call that look, no Z. So doing that, inputting X and Y, it's able to forecast in red the Z. So X and Y with delays, no Z's. Okay, that's not a surprise to anyone who knows Topkin's theory, but here's a way to implement that really well. That a few variables know the rest of the variables in some sense in some diffeomorphic form. That's what Topkin says. But here's kind of a very practical way of doing this in a machine learning formalism. Okay. Benjamin Wasselhauser, a student I've been working with, an undergraduate student, very, very sharp undergraduate student. We've been predicting spatial temporal data. This is sea surface temperature data from Earth, which we do by forming lots of reservoir computers, one for each measured point as a vector process, which is like a patch. This is a picture of a patch, which we also kind of compensate the patch so that when there's land, we don't try to predict sea on the land. So we have to kind of make an adjustable size patch. And then some kind of like boundary region which couples the patches together. So rather than forecast the whole thing as one massive high dimensional process, you have a lot of little RCs that are coupled to each other. And it does a really nice job of forecasting the sea surface temperature into the future, both the temperature, and I also showed you that the error stays small for a rather long time. So that we just put out like last month. Okay, here's a different, this is the last little bit of my talk. Here's a different version of where does all the random go. I kind of showed you that in my first interpretation is random kind of gets soaked up by time. All the column, it gets soaked up into the column spaces of compositions of the matrix. So it gets soaked up by time. Another interpretation of this is to think in terms of concentration of measure, meaning the Johnson-Linden Struss theorem. So this is kind of a magic theorem. I'm still amazed when I think about it. I was amazed when I first saw it, and I've learned it a few years ago, but it still amazes me. And it's based on the idea of concentration of measure that goes like this. So suppose you've got high dimensional data. The high dimensional data looks mostly flat, says Johnson-Linden Struss. So suppose this is a description that's in this book by Matusek in 02. It's a beautiful book. So suppose I've got a two-dimensional sphere living in 3D. So I would draw a strip of width h like this, and I could ask how big is h to pick up, say, 90% of the sphere. or X% of the sphere, right? So how thick is it? So in 3 dimensions, so D is 3 for S2, the 2-dimensional sphere, this is the strip that picks up 90% of the area of the sphere. And in 11 dimensions, this is the strip. The H got smaller. And in 101 dimensions, this is the strip, the H got smaller. So this is 90% of the sphere for it has a small H for high dimensions. And you can make a formula, this asymptotes to 0. So for very high dimensions, the height of a strip that picks up 90% of the area becomes increasingly small. And what that means is if I had a distribution that selects points randomly in the sphere, then I may say, show me 90% of them with overwhelming probability in 101 dimensions, they'll be in a thin strip. And that has implications of how data is distributed in high dimensions. So this idea leads to a lot of kind of central theories, like in analysis and inequalities, like the Markov inequality can be interpreted in terms of this discussion. The Chernoff inequality can be interpreted in terms of this discussion. But the part I'm interested in is the Johnson-Linden Struss theorem. So in high dimensions, samples of data look almost flat. So this is a picture of what the story is for the Johnson-Linden Struss theorem. So suppose I take a random sample of data points in high dimensions, like think 1,000 dimensions, and I ask what's the distance between any 2 pairs, the exact distance, and usually L2 norm. Then if I project the data to a low dimensional space, I'll make it almost the same answer with many projections. So think of this as like a flatter space than the true space. And typically there's a very flat space where this is true, where L is much lower dimension than N, where L is the dimension of the flat space. So this is what's called an approximate isometry when it's almost equal. So here's how you really say it for the Johnson-Linden Struss theorem. So it says so you choose your error, epsilon, and F can typically be a linear projection, but a measurement of the data X in the original space, the distance between them, is almost the same as the original, except wrong by an 1 plus epsilon or 1 minus epsilon, right? So you get almost the right answer. And an inequality like this is called a approximate isometry. And the point of this is that the dimensions that work well is related to the error you're willing to make and the number of points you have. And in this, it's a logarithm of that number of points. And this ends up being a really strong compression for a relatively small epsilon to almost correct distances. So this version of the Johnson-Linden Struss theorem can be reinterpreted this way. So that was 84 by Johnson. Reinterpreted this way in terms of random matrices. So with overwhelming probability, you'll get something a lot like this, but just stated this way. You'll get an approximate isometry for random matrices, and one version of this could be normal random matrices for a not square matrix. So that's what I mean by projection. You project the data. So this will be a good picture for random matrices. So randomly sampling. So Sudham, who you just saw talking, used this to interpret DMD.
Excuse me, we are running a bit out of time.
Okay, I can get through this in about
2 or 3 more minutes.
I can get through this in 2 or 3 minutes.
Yeah, thank you.
So you typically do Koopman on data by making X matrices, and you fit a DMD matrix by doing least squares. What we're asserting is you can do a random projection instead to a lower dimensional data set, and that could be correspond also to subsampling, downsampling, and also to the outcomes, and fit a K to that. And somehow when you do that, you get the right answer in some sense. I'll make that precise in a minute. but I'm just a little long on telling you the detail of this pretty picture, but it just means project randomly, subsample, fit a K matrix to that, meaning a DMD to that downsampled guy, and it's useful. So that's what the algorithm says, but mostly it says take your original data and choose a random projection matrix, and so from normal distribution, and downsample by that random sampling matrix. And you can do things like finding eigenvalues, eigenvectors, and those tell you something about the true system. So the eigenvalues and eigenvectors are what you talk about, frequencies and also modes. So, and just by leveraging Johnson-Linden Struss theorem, you can actually tell how big is the error and so forth. So that's what's in that last paper I mentioned to you is building inequalities like this that bound the error. But I'm just going to show you like a punchline picture or two. This is from this is the Mediterranean Sea. I'm sorry, it's the wrong one. I'm looking at the wrong one. This is Florida, the United States. This is Cuba, and this is the Gulf of Mexico. And you can think of this as flows of the ocean from a high dimension, a high precision model called ROMS of the ocean. And this is modes from a full DMD, and this is modes from a random version of downsampled version of the DMD. And you can see they make almost the same thing. And they make almost the same thing in just the way promised by those inequalities I showed you. So this is some of the modes. This is another set of modes. They pick up almost the right frequencies. They pick up almost the right spatial form and so forth. So we call it RDMD, the random version of the DMD. And it's really useful because it has implications for actually lower frequency. Okay, so it tends to give good pictures for other modes and in general. And I'm gonna end with saying that, okay, we have that. So it should actually connect back to the NGRC as well, because in a way, this is a very similar kind of a reduced order model in a way like random projection, because we're downsampling. That part we haven't done yet, but you can see the connection. So this is literally my last slide there. And there's just a bigger version of our winter scene picture I took last weekend. So thank you.